Binomial Distribution, Book 1. By Professor A. Ramachandran. Lesson Objective 1. Introducing Bernoullian experiments. 2. Deriving the binomial distribution. 3. Characteristics of the binomial distribution, moments and other constants. Engineering applications of the binomial distribution will be discussed in the second book of the series on binomial distribution. The book is expected to serve as a tool, introducing the binomial distribution to the readers. Prerequisites. The science of statistics deals with random variables and their distributions. Random variables come under two broad categories, namely, discrete random variables and continuous random variables. The binomial random variable is a discrete random variable. Distribution is an act of assigning, distributing. For example, if a sum of r'(s.100/ is given to be shared by 10 people, we say that as distributing the money. The teaching workload is distributed among the teachers in the department. In a similar manner, the total probability 1 is always distributed among the different values assumed by the random variable. How this distribution is done is explained by the probability distribution function. If the random variable being discussed is a discrete random variable, the distribution is known as probability mass function. If the random variable being discussed is a continuous random variable, the distribution is known as probability density function. If the set of values assumed by the random variable is countable, it is a discrete random variable. A random experiment is an experiment in which the outcome of any trial cannot be predicted in advance. The outcome can vary from person to person, time to time, or place to place. If every possible outcome of a random experiment is assigned a numerical value, a real number, we can see that a random experiment generates a random variable. As mentioned earlier, if the set of values is countable, it generates a discrete random variable. If the set of values is uncountable, it generates a continuous random variable. A random variable is a variable that takes different values, and, for every value of the random variable, there is a corresponding probability, and the sum of all the probabilities is always equal to 1. A Bernoullian experiment is a random experiment that satisfies the following conditions. 1. There must be n independent trials. 2. Each trial has only two possible outcomes, a success or a failure. 3. The probability of success in any trial remains a constant throughout the experiment. Events are said to be independent if the outcome of one event does not, in any way, affect or influence the outcome of another event. For example, during election times, election is conducted in several states at the same time. If the result of one state does not affect or influence the result of another state, it is an example of independent voting. During examination times, several students write the examination for the same subject. If the result of one student does not affect the result of another student, then it is an example of independent event. Let us now discuss certain experiments to find if they can be called as Bernoullian experiments or not. A set of students appearing for an examination. The first condition that there must be an independent trials is satisfied as there are more than one student appearing for the examination. The second condition is also satisfied because for each student trial, there are only two possible outcomes, success or failure. The coin is tossed n times. Thus there are n trials. The trials are independent because the outcome of any trial does not affect the outcome of any other trial. Thus, the first condition is satisfied. For any trial, there are only two possible outcomes, namely, a head or a tail. Thus, the second condition is satisfied. Since it is a fair coin, the probability of getting a head in any trial is 1/2 and remains a constant throughout the experiment. Thus, the third condition is also satisfied. Since all the three conditions are satisfied, tossing fair coin n times is an example of a Bernoullian experiment. Consider the simple experiment of tossing a coin, say 100 times. Let us further assume that the probability of getting a head in any trial is P and probability of getting a tail in any trial is Q, so that P plus Q equals 1. Let x be the random variable whose value is given as the number of heads obtained on tossing the coin 100 times. X is defined as the number of heads obtained on tossing the coin 100 times. Hence, the possible values of x are 0, 1, 2, 3, 4, 5, 99 or 100. X equals 0 implies that every time the coin was tossed, the result was a tail. X equals 1 implies that out of 100 tosses, the head was obtained once and tail in the remaining 99 trials. Similarly for other values of x.
Hello everyone, have you ever read in the newspaper or on the internet about some amazing coincidence or unlikely event, and it will say something like, oh, it was a 1 in a million chance, but still, it happened? Well, the point is, even unlikely events will happen if you give them enough opportunities. For example, flipping 10 heads in a row. Well, that's about 1 in 1,000. Well, in fact, it's a half to the power 10, which is 1 in 1,024. Now, if you perform the experiment 1,024 times, you might expect it to happen once. In fact, you may have seen the magician Derek Brown try this, and it took him 9 hours. Now, was he lucky or unlucky? Let's find out. I'm going to do it. Here's my coin. I'll show you. There's the queen there. There's the queen's face. On the other side, there's the tail, which I've marked with a big X cross. No, this is bad. This is the fail tail right there. Now, let's try it out. This is my first attempt. I'm going to flip the coin into the bowl. And I get a tail. Not a good start, but still, that's 1 down, 1,023 to go. And that's exactly what I did. Trial after trial, coin after coin, continuously flipping the coin until I got 10 heads in a row. I knew most of my attempts would not be successful. In fact, the vast majority, nearly 90%, would end on only the first, second or third trial. On the plus side, that meant I could stop the trial as soon as I saw a tail, which meant I could save a lot of time. Even so, like Derek Brown, I was fully prepared that 1,024 attempts would take 9 or 10 hours. Yet it's even worse than that. If I tried the experiment 1,024 times, I expect 1 success. But that's an average. I might get 3 successes, I might get 2. On the other hand, I might fail completely. I might try 1,024 times and fail every single time. In fact, I knew that if the probability of success was 1 in 1,024, then the probability of failure is 1,023 in 1,024. And the probability of failing every time would be that to the power 1,024. That's the number of trials I intended to perform. That means the probability of total failure was about 37%. Success then was 63%, but in no way guaranteed. But I kept trying and trying until 1 hour in, and on trial 234, heads. 2 heads. 3 heads. 4 heads. 5 heads. 6 heads. 7 heads. 8 heads. 9 heads. 10 heads. 10 heads in a row. Success, and much sooner than I expected. So I could have stopped right there, but I decided to complete the experiment to finish the 1,024 trials. But since I had already had 1 success, did that mean I wouldn't get another now? Well, I knew that wasn't true because a coin has no memory, and success in the past would have no effect on success in the future. Even so, I only had 790 trials to go, so I knew the probability of total failure from this point on would be about 46%, meaning I still had a better than half chance of another success. Yet, unfortunately for me, in the next 5 hours, no further luck. But it does go to show that even unlikely events happen if given enough opportunities, even if you can't predict exactly where and when they happen.